Today we will see a very important topic that is called capacitance. What is capacitance? Capacitance is the ability of a body or a device to hold electric charge. In very simple words. What is the meaning of this? See, we have only three electrical elements. Whenever we analyze a circuit or we analyze a device, we have only three basic circuit elements. First is called resistor. From resistance, any device that offers resistance is a resistor, and I am talking for electricity only. Second is capacitor. This is from capacitance. And third is inductor, from inductance. If you take a wire and you pass electric current through it, it will offer certain resistance. So we make devices that offer resistance as per our requirement. If we require a resistance of 2, the unit is ohm, we'll take a material that will offer 2 ohms resistance at its node, and this will be our device. Whatever it be, I'll explain to you later on. Similarly, we have capacitance. What is capacitance? I told you it is the capacity of a body or a device to hold electric charge. So let's say this is a body and we are able to put an electric charge of Q on this body by applying voltage across it. Why do we apply voltage? We apply voltage to create electric field. So if we apply voltage, let's say this is minus, this is plus, so we apply voltage to it so that Q charge is accumulated on this device, on this surface. We say Q by V, this is a constant which is C. That is, capacitance is defined as Q by V, the total charge accumulated, or the charge that the body is holding, and the voltage that we have applied through across it. So this is C. You should remember this. C is Q by V. That is directly proportional to Q and inversely proportional to V. Okay. So this is capacitance. We usually denote it as R. We denote it capacitance as C and inductor as L. Then we have third device, which is called inductor. The property is inductance. It is because of electromagnetic interactions within a body that we'll study after studying circuits that have resistance and capacitance. Then we'll get into electromagnetism, and then we'll understand what is inductor. Why I have given or why I have discussed all the three here? Because any electric circuit can be analyzed as a combination of resistance, capacitance and inductance. Let's say we have, this is tower. Wires are going from one tower to another tower, then they go to a transformer. This is a transformer, then they reach home. Okay, now at this point, if you take 2 points, the input point, you can view this whole setup as, I'm redrawing it here, this is A, this is B. So if you take AB, you can say it is R plus C is denoted like this, capacitance, and inductance is denoted like this. So you can represent this whole setup as R, C, L. How we represent, we'll see. From time to time we'll be studying different topics, and then finally when this will be over, we'll be able to analyze any circuit. We'll be able to analyze any device and any circuit. Even if you have a television, there are so many devices inside it, but every device, let's say this is an IC, integrated circuit. You must have seen this. It is like this. It is made up of transistors. It is generally like this. And this transistor has these three properties: resistance, capacitance and inductance. So what I told you in the start only, we have only three basic electric circuit elements: resistor, capacitor and inductor, and the properties are called resistance, capacitance and inductance. So let's come to our topic. What is capacitance? I told you the definition. C is given as Q by V. I am not getting into qualitative discussions now. We'll have very qualitative discussions after 2-3 classes. First of all, let's understand how to use a capacitor in a circuit, and what is a capacitor, how it behaves in a circuit. This is our first priority. Then we'll get into the qualitative discussions on capacitance. C is Q by V. How we denote it? We denote it by this parallel line. This is your capacitor. Now let's start with a parallel plate capacitor. You know, if we have an infinite sheet, the electric field near this sheet is given as sigma by 2 epsilon 0, and you have n cap, that is, this is your n cap. If this is the sheet, this is normal to this. This we have discussed in our earlier videos. You must have worked this by yourself also. So let's understand. If we have two parallel plates, these are sheets. Let's say the area is A of one parallel plate, one plate. The area is A. That can be a circular disc, or it can be a square, a rectangle, whatever it be. The area is A. The charge is Q on this. Let's say this is Q charge. Since this has Q charge, we have connected it to, this is plus minus a battery V. Obviously, negative charges will be induced on this plate. Okay. Now, electric field due to this will be in this direction, because it is always from positive to negative side, and this is negative. Electric field due to this at any point will be also in this direction, so that both electric fields will get added. Clear? Electric field due to this, if this is the distance d, d is the distance between the plates, which is very low compared to, very less compared to the length of this particular, the area of this plate. Then electric field due to this plate near this surface, that is from here to here, will be, let's say, E. This is E. So it will be like this. E will be sigma by 2 epsilon 0, where sigma is what? Q by A, surface charge density, and epsilon 0 is permittivity of the space or vacuum. Now, electric field due to this will be similarly in this direction only, because this is negative, so from positive to negative, so this will be E. So what will have? Net electric field will be, net electric field at any point will be twice of E, E due to this and E due to this, E plus E. So this will be twice of this. So what you finally get is, I am rubbing now, electric field intensity, you will get sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. So what you get is sigma by epsilon 0, and direction, you know, this is the direction. If n denotes this, this is the direction from positive plate to negative plate. Given this distance is very small as compared to the area of this plate, that is d square, because whether it be a disc or a rectangle or whatever, it will be, area will be square. So d square is very less than A. This is the condition. So we have electric field. We have defined electric field is sigma by epsilon 0 n. Okay. Now I told you Q by V is C, but we need to know the relation between V and E, so that we get a formula for capacitance. See, V is what? V is electric field intensity, magnitude of electric field intensity into the distance. You know this. Why? Because E is given as del V by del X minus, it is the gradient. The electric field is a gradient of potential, spatial gradient. So E into D. So what we do from here, V is equal to Q by C, and V is equal to this into this, that is sigma D by epsilon 0. Clear? So what we get is, C will be, C can be written as Q epsilon 0, see, Q epsilon 0 by sigma D. This is the value of C. And you know, in terms of sigma and Q, what is sigma? Sigma is Q by A. So Q epsilon 0, this is Q by A into D. So Q cancel. So what you finally get is epsilon 0 A by D. This is your capacitance. From here you get a very important result, that the capacitance of this capacitor, this parallel plate capacitor, depends only on its geometrical features, geometrical characteristics. That is, it depends on the area of this plate and the distance between these two plates. It does not depend on any other value. It is dependent only on the geometry of this capacitor. This is a very important observation. Okay, so capacitance for a parallel plate capacitor is epsilon 0 A by D. Okay. So I think this is clear. I'll discuss dielectrics in the next video what is the meaning of dielectric. For the time being, we have assumed that this is vacuum. The space between the two sheets is vacuum. What if a dielectric is placed? What if air is placed? What if we have a wood inside it? What if we have some plastic inside it? We'll discuss it in the next video. For the time being, let's understand what is a capacitor, and we'll see what is a capacitor when placed in series and when placed in parallel. Okay, so let's see what will be the net capacitance or the total value, the net value of the capacitance when it is connected in series and when it is connected in parallel. See, capacitors connected in series. What is this? Let's say this is capacitor 1, C1. It is connected to another capacitor, C2. This is connected to third capacitor, C3, and so on. We have the relation C is Q by V, that is CV is Q. This you should keep in mind. So we have C1, C2, C3. The charges you can take Q1, Q2, Q3. Now, if we apply a voltage V across it, if V is applied across this, then let's say V1 is developed across C1, V2 is V2 across C2, and V3 across this. Okay, clear? This plus this plus this. Now we know that V will be equal to V1 plus V2 plus V3. This is total V. So this plus this will be equal to this. And from here, what you see? V is Q by C. That is, it will be equal to Q1 by C1 plus Q2 by C2 plus Q3 by C3. And for V, you can write it is Q by C, net capacitance. This is clear up till now. Now try to understand. If we have a parallel plate capacitor, this one, we have charge here and it is connected to another capacitor. This is what is here. I am redrawing it here. So this will be plus minus plus minus plus minus. We have applied voltage. Here we have used 3 capacitors. If the charge accumulated on this be Q1 and on this be Q2, if there will be a difference of charge, then if let's say Q1 is greater than Q2, what we'll get? We'll get from Q1 to Q2, this will be the difference of charge. This will start conducting. It will go to this point because it will stop only when there is an equilibrium. That is, when the capacitors are connected in series, the charges on each of them will be equal. Why? Because if the charge on this is Q1 and this is Q2, if Q1 is greater, it will conduct. That is, charges will start flowing to this capacitor until the two become equal. This will repeat for every capacitor in series. That is to say that finally what will happen, that all charges will become equal to certain value, let's say Q. Clear? This will be constant. Why? Because if the charges are different, we will have conduction of charge from one capacitor to another until it reaches equilibrium. That is, charge on the two plates are same, so that finally we have equal charge. Clear? So we have this as Q, 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 that is the whole charge. So from here what you get? Q, Q, Q cancel. So what you finally get is 1 by C is equal to 1 by C1. 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3 and so on if you connect n number of capacitors. That is, we can replace this by an equivalent capacitance which has capacitance equal to C. That is where 1 by C is 1 by C1 plus 1 by C2 plus 1 by C3 and so on. So when capacitors are connected in series, we have net capacitance or equivalent capacitance equal to this 1 by C equal to 1 by C1 plus 1 by C2 and so on. Clear? Now, when the capacitors are connected in parallel, then what? Let's see. If capacitors are connected in parallel, it means like this. We have one capacitor here, then one capacitor here, another capacitor here and so on. These are connected like this. They are connected. That is, voltage across them is same. If we apply voltage V, so voltage across this capacitor, let's say C1 will be V, across this will be V, across this will be V, that is this is plus minus V, plus minus V, plus minus V. Obviously, we know that Q is CV. Since capacitances are different, different charges will be accumulated over the different capacitors. That is, Q1 on this capacitor will be C1V, Q2 will be C2V, Q3, C3V, and no. Okay. And what will be the total charge? The total charge, let's say Q, we can say this is CV, where C is the equivalent capacitance. That is, if we replace this whole network by an individual capacitor, this will be equal to Q1 plus Q2 plus Q3 and so on. That is C1V plus C2V plus C3V and so on, if we have n number of capacitors. So from here we cancel V, C equivalent capacitance is equal to C1 plus C2 plus C3 and so on. So when capacitors are connected in parallel, the net capacitance will be C1 plus C2 plus C3. That is, we can replace this whole network by a single capacitor only. So let's see how to solve examples, simple examples. We are building up concept here, so just be with me. If in a parallel capacitor, area is, let's say, 2 meters square, the area of one sheet is, the distance between the two plates is 2 centimeter. That is, in terms of meters, you can write it like this. And we have to find capacitance of this. I told you this is epsilon 0 A by D. So this is 8.85 into 10 to the power minus 12 Coulomb square per Newton per meter square, the SI unit. Area is given 2 meters square. This is 2 into 10 to the power minus 2. So 2 cancel. What you get is 8.85 10 to the power minus 10. So you can write, okay, this is coulombs. You can write it in pico and farads also, and not coulombs. I saw C and write. The unit is Farad. The unit of capacitance is Farad. Okay, so this is 8.85 into 10 to the power minus 10. So very simple. It will get complex when we will start exploring different types of capacitors. We will see it later on. Then let's see. We have simple one, 3 capacitors, C1, C2, C3. This is A, this is B. Let's say this is 2 Farad. Farad is a very big unit. You have capacitance in micro nanofarads, but let's say, for example, 2, 3 and 4 farads. What is the equivalent capacitance? So you know, in case of series, 1 by C will be 1 by C1 plus 1 by C2 plus 1 by C3. That is so what you get is 26 by 24. Okay, so C is 24 by 26 farads. Okay, now let's say the same are connected in parallel, that is like this. This is A, this is B. Then what? Then you know it is just C will be, equivalent capacitance will be 2 plus 3 plus 4. That is 9 farads. Okay. Now let's see a bit complicated one. A bit complicated, not so complicated. Let's say this is 2 farads. Then we have up like this. So this is A, this is B, this is C. Let's say this is 3 farad and this is 4 farad. What will be the equivalent capacitance across AC? Let's say what will be the capacitor. This is C1, this is C2. What is C2? C2 will be simply, these are in parallel, so 4 plus 3, 7 farads, and this whole capacitance. So this will be, this is in series with this, so this and this, so 1 by 2 plus 1 by 7. Okay, so this is, so your capacitance is 14 by 9. Okay, so what I advise is, go to your textbook and solve simple examples on this. Don't worry, we'll solve examples that are very complicated, but later on in our next videos. For the time being, you go and solve simple examples so that you build concept.